Good afternoon. So now we will study how to Nortonize a network or the circuit. We are saying that according to Norton's theorem, any complicated network, two-terminal linear network, can be simplified in terms of a current source in a parallel with an equivalent resistance called Norton resistance. So this complicated network to the left of the terminals A and B can be simplified in terms of a constant current source in parallel with the equivalent resistance. So for that purpose, to Nortonize this network, this procedure consists of the 4 steps. The first step is disconnect the load resistance RL from the terminals A and B. In the first step, we have to remove this load resistance from the terminals A and B. The network we get is of this type. When the load resistance RL is removed from the terminals A and B, the network we get is of this type. So here we have to first find out the values of IN and RL. So first to find out the value of IN, what we need to do is we have to, this IN is nothing but the current that will flow through a short circuit put across the terminals A and B. So in the second step, what we need to do is put a short across AB and find short circuit current. Find the short circuit current. So when we put a short across the terminals A and B here, and when we want to calculate the short circuit current ISC flowing through this short circuit, what happens is the resistance R2 gets short circuited. The resistance R2 gets short circuited. So the current ISC that will flow through this short circuit put across the terminals A and B will be equal to simply E upon R1. E is given to be 10 volt and R1 is 4 ohm, so that the current IN will work out to be equal to 2.5 ampere. The current ISC will work out to be equal to 2.5 ampere, and this short circuit current is nothing but the Norton current IN. So IN is equal to 2.5 ampere. So this is the value of a constant current source IN, and in the next step we want to find out the equivalent resistance RN. So step 3 is remove the short from the terminals A and B, such that they are again open circuited, and replace battery by its internal resistance. In this case, no internal resistance is mentioned here, so the internal resistance to be considered here must be 0. So when this short circuit is removed and the source of EMF is replaced by its internal resistance, the network will take the form like this. This is the resistance R1, the resistance R2, and we have the terminals A and B again open circuited. The terminals A and B are open circuited, and we have the resistors R1 and R2. The source of EMF is killed for its EMF, retaining its internal resistance in the circuit. So in the given network, this source does not have any internal resistance, so it is 0. Now, the value of R equivalent is nothing but the resistance of this network when viewed backwards from the open terminals A and B, and when we view this network backwards from the open terminals A and B, it appears to us that the resistors R1 and R2 are in parallel. So we have R equivalent is nothing but the equivalent resistance of the parallel combination of R1 and R2, and we know that the equivalent resistance of the parallel combination of R1 and R2 is given by R1 R2 upon R1 plus R2. So using the values of R1 and R2 here, so it gives 4 into 6 divided by 4 plus 6. So 24 by 10, so it is 2.4 ohm. So R equivalent works out to be equal to 2.4 ohm, and this R equivalent is nothing but the value of Norton resistance Rn. So Rn works out to be equal to 2.4 ohm. So we have found out the values of In and Rn. So once we know the values of In and Rn, now we can draw the Norton equivalent circuit for the given complicated network like this. So the Norton equivalent circuit for the given complicated network will consist of a constant current source In in parallel with an equivalent resistance called Norton resistance Rn, and we have these terminals A and B. The value of In we have found out is 2.5 ampere, and the value of Rn is 2.4 ohm. And again, if we reconnect the load resistance RL between the terminals A and B, now we can find out the current IL flowing through this load resistance RL. We can find out the current IL flowing through this load resistance RL. The value of RL is given to be 5 ohm. So by using the current division formula, inverse current division formula, the value of IL is given by the expression IL is equal to Rn upon Rn plus RL into the total current sent by the source, that is IL. So using the values of Rn, RL and IL, Rn is 2.4 ohm divided by 2.4 plus RL is 5 ohm multiplied by IN is 2.5 ampere. So if we solve this, it works out to be equal to 0.81 ampere. It works out to be equal to 0.81 ampere. So that is how we can find out the current flowing through the load resistance, and once we know the current IL flowing through this load resistance RL, and that is what we want to obtain. So that is how we can Nortonize a given network. Nortonizing a network is nothing but to obtain the current flowing through the load resistance, or knowing the value of load resistance and current flowing through it, we can as well find out the potential difference across the load resistance. So that is how we can Nortonize a given network. So that is about the Norton's theorem and how to Nortonize a given network. Once again, you can listen to the Norton's theorem, which states as any two-terminal linear network containing sources of EMF and resistances can be replaced by an equivalent circuit consisting of a constant current source IN in parallel with an equivalent resistance called Norton resistance. So this network is the Norton's equivalent circuit. So the value of IN is nothing but the short circuit current that will flow through this short circuit put across the terminals A and B, and the value of Rn, equivalent resistance, is nothing but the resistance of the given network when viewed backwards from the open terminals A and B, when the sources of EMFs have been replaced by their internal resistances. So that is about the Norton's theorem and how to Nortonize a given network or a circuit. Okay, thank you.